Thank you for tuning in. So to introduce myself a little bit, I am a Gavin Fellow in Exoplanetary Science at the Institute of Astronomy in the University of Cambridge in the UK. And my main area of research has to do with observing giant planets with long baseline interferometry. And I am mainly working within the Exogravity Large Program, which is a large program on the Very Large Telescope Interferometer dedicated to observations of exoplanets. And so with this program, we've observed a number of planets so far, and we've obtained a number of high precision astrometric measurements on exoplanets, which I am going to talk about later on in this talk. But this is, of course, directly related to the topic I'm going to discuss today, which is finding planets with astrometry. And before I jump straight into the subject, I think it's good to say a few words about the method and to set the scene. So this idea of finding planets by looking at the reflex motion of the star isn't something new. It's actually quite an old idea. But to say the least, the beginnings of this method weren't really great. A number of planets have been claimed in the past with this method, which turned out to be false detections. And so I recently came across a book. It's called The Crowded Universe. It's written by Alan Boss. It was published, I think, in 2009. And it's not just about astrometry. It's really about the history of exoplanet observations, the beginnings of the field. But there is a part in the book where the author talks about astrometry. And it's interesting because Alan Boss is an astrophysicist. So the book doesn't talk only about the methods and the results, but it also gives sort of an inside view. And when he talks about astrometry, so he explains that a number of detections have been claimed in the past, which turned out to be false detections. And then he writes about astrometry. He writes that astrometric planet detection acquired a reputation as a dubious enterprise, rather like the search for life on Mars, which was associated in astronomers' minds with the claims for Martian canals that must be sign of an intelligent civilization on our neighboring planets. Then he goes on and he says, proper astronomers did not stoop to looking for planets or searching for life in the solar system. So that was written in 2009, which I think is interesting, and it raises one question, of course, is what is different now? I mean, we went from this state of mind, probably in the 2000s, to today, where we have a dedicated talk on astrometric planet detection at the Sagan summer workshop. So something must have happened, of course. And I think there are two main reasons for this change, which are related to two instrumental progress, basically. So the first one, of course, is the advent of space-based observatories. Astrometry is extremely difficult to do from the ground, of course, because of the atmosphere. It's much easier to do this properly from space. And so, of course, the fact that we now have even dedicated space-based observatories to do this, and I'm thinking of Gaia, of course, really changes the situation. And the second one is long baseline interferometry, which we now have long baseline interferometers which are working very well. And from the ground, long baseline interferometry is one of the methods which can give the best results in astrometry. You can get really high precision measurements with this technique from the ground. And so those two different methods to do high precision astrometry are basically going to be the two parts of my talk today. So I'm going to talk mainly about this combination of Gaia and Hipparchus data, which are two space-based observatories. And combining those data can lead to the detection of new planets. So that's something I'm going to discuss quite extensively, actually. And then in the second part, I'm going to focus on gravity and what long baseline interferometry can also bring to this topic of finding planets with astrometry. So Gaia and Hipparchus. So Hipparchus is a satellite which was launched in 1989 and operated until 1993. It's a European satellite, and the mission was to get high precision astrometric measurements on a number of stars. I think the last catalog has something like 2.5 million objects in it, but there are only, there are only 118,000 stars on which high precision astrometry was obtained. And today we have another mission, was launched in 2013 and it's still operational, which is Gaia. This is, of course, a much more recent satellite, and the number of targets is huge, and the precision obtained is excellent. So this is really, I think, the combination of those two missions is really the foundation of what I'm going to discuss today. I think it's fair to say that if it wasn't for Gaia, we wouldn't be talking about this probably. It really changes. It changed many things in the field of astrometry. So, how do we detect planets using Hipparchus and Gaia and astrometric measurements? So, one method, which is probably the most used, so the idea of astrometry is looking at the reflex motion of the star. So if you have a star in yellow here and a planet in blue orbiting around it, so the planet isn't orbiting around the star, it's orbiting around the center of mass of the system, which means that the star itself is also orbiting around the center of mass. So there is what we call a reflex motion of the star caused by the presence of the planet. Now, of course, the whole system can have its proper motion. So the whole system can have a motion on the star. And so the motion of the star is going to be a combination of the two, combination of the reflex motion caused by the planet and the long-term motion of the system. So using Hipparchus and Gaia data, it is possible to measure this motion. And one thing you can do is, so Hipparchus obtained astrometric measurements on stars in, I think the reference epoch is 1991, whereas Gaia obtained measurements at a reference epoch, which is 2016, at least for DR2. So if you take the astrometry of the stars obtained by Gaia, you subtract the astrometry from Hipparchus and you divide by the time between the two, which is about 25 years. Then you get a measurement of the proper motion, the long-term proper motion of the system. So the velocity, basically, of the system on the sky. Now, that's not the only measurement you have. If you look at the Gaia data, you also have a measurement of the, say, instantaneous proper motion. And this instantaneous proper motion is actually a combination of the long-term proper motion, which I call here mu star, and the reflex motion or the orbital proper motion, the orbital motion of the star. So if you take this instantaneous measurement made, for example, by Gaia, and you subtract the long-term proper motion which you get from the difference between the two catalogs, then in principle, you should have a measurement of the orbital component of the motion. And this quantity, the difference between the instantaneous motion and the long-term proper motion, is what we call the proper motion anomaly. And the idea is, if you have a star without a planet, then the instantaneous proper motion and the long-term proper motion should be equal. And this quantity, the proper motion anomaly, should be zero. Whereas if you have a planet or another companion orbiting around the star, you should see this as a proper motion anomaly. Now you can calculate a proper motion anomaly at the Gaia epoch using the Gaia instantaneous proper motion. You can also, of course, do this at the Hipparchus epoch, and then you would get a proper motion anomaly at the Hipparchus epoch. And then from this, you can start to look for companions to stars. So if we look at the order of magnitudes, if you take a sun-like star at 10 parsec and a planet of 1 Jupiter mass orbiting at 1 astronomical unit, then the typical velocity, the orbital velocity of the star is going to be something like 30 meters per second, which translates to 6 milliarcsecond per year on the sky at a distance of 10 parsec if you take the orbit face on. If you go to 5 astronomical units, then you have something which is more like 0.26 milliarcsecond per year. Now, this motion, its orbital motion scales as the mass of the planet, the inverse of the square root of the mass of the star. So it's easier to look for planets around small stars with this method. It also scales as the inverse of the square root of the separation, and of course the inverse of the distance, simply because of the geometrical projection. But then if you look at the catalog and you do the calculations, then the typical precision in DR2, actually, I don't know in DR3, but the typical precision on the proper motion normally depends on the targets, depends on many different factors, but it can range anywhere from 0.5 to 5 milliarcsecond per year, typically. On some targets, it's even better than this. On some other targets, it's worse. But that's the typical ballpark, which means that with a method like this, basically, we can expect to find planets of, say, a Jupiter mass. That's the typical order of magnitude, maybe a bit more. If the star is close to the sun, then we can hope to find less massive planets. But that's the typical order of magnitude. Now, so I did the exercise to prepare this presentation. I used a paper which is dedicated to this idea. It's a paper by Cavella and colleagues in 2019. And I tried to reproduce some of the results. So basically, my question was, how hard is it to do this, to use the Hipparchus and the Gaia data to try to find, calculate proper motion anomalies and find planets? And the answer is, it's actually not very difficult. And I think one of the reasons for this is where, of course, first, other people have done that before. So I basically, in my case, I just followed the recipe pretty much. But also, other people have done the hard work, actually. If you look at the Gaia and Hipparchus catalogs, those catalogs are very easy to use because other people have done all the data reduction and all the difficult work. So if you want to get a proper motion anomaly, the recipe goes like this. Typically, you take your targets. So, for example, I used 51 peg as my target. You get the Hipparchus number from Simbad, for example. So you can easily do this in Python using, for example, Astrometry. So you get the Hipparchus number, and then you need a way to get the corresponding Gaia ID number. So I think there's a number of ways to do this. I think you can even get the Gaia ID from Simbad. But in my case, I used a catalog published by Brunt and colleagues in 2018, where you have the cross-correlation between Hipparchus and Gaia. So from the Hipparchus ID number, I could get the Gaia ID number. And once you have the two IDs of your targets in the two catalogs, then you can query the two catalogs. You get the astrometry in proper motion at the two epochs. Then there is a little bit of cooking, at least for DR2, for Gaia DR2. There's a little bit of cooking to correct the Gaia data, but it's not very difficult. Then you can play a little bit with the parallax. The parallax from Gaia is much better than the parallax from Hipparchus. So you can, basically you can back propagate the Gaia distance using radial velocity data to the Hipparchus epoch and replace the Hipparchus parallax by this number. Can be important because of the geometrical projection of the velocity of the star, which changes depending on the distance. And once you have all this, then you can calculate basically the velocity vector of the star in the ICRS frame, and then you project this on the sky to get really the proper motion. So you project this at the reference epoch of Hipparchus and at the reference epoch of Gaia, and then you can calculate the proper motion normally. So it's, yeah, basically you can do this in less than 70 lines of code, and you get, so it's not, yeah, it's probably not paper grade results, but it works, and you can get proper motion anomaly measurements with something like this. So relatively straightforward. So once you have a proper motion anomaly measurement, what can you say about the planet? So actually, I've shown that the proper motion anomaly is, so if you know the mass of the star and you know the distance, and you do have the distance actually, at least from the Gaia data. So if you know this, then the proper motion anomaly is actually a measurement of the mass of the planet divided by the square root of the semi-major axis. Now, of course, this is valid for a circular face-on orbit. If the orbit is inclined or if you have some eccentricity, then this isn't really true, and you need to take this into account. So then it depends on what you're doing. From a statistical point of view, you can expect the inclination, the eccentricity, and all of this to reduce your measurement typically by a factor of 0.87, which means that if you're interested in the statistics of the proper motion anomaly on many different targets, you can pretty much just multiply your measurement by 1 divided by 0.87, and you'll get a decent result. If you're interested in one particular target, then you need some way to be able to take into account the true inclination, and I'm going to talk about this later on. But that's the idea. So once you have this, in principle, you have a measurement of the mass of the planet divided by the square root of the semi-major axis. Now, it's not as easy because there are a number of issues with the method. One of which is the fact that neither Gaia nor Hipparchus measured the true instantaneous proper motion. To reach the level of precision needed for this, those missions actually averaged a number of measurements. And typically measurements were taken in Gaia DR2 over 665 days, and Hipparchus over a bit more than 1,200 days. And the problem with this, of course, is if you have a small period planet, so a planet orbiting with a period which is smaller than typically 665 days for Gaia, then averaging the measurement of the velocity at different times changes the result. It decreases the measured velocity simply because this velocity vector is rotating with time. So if you add all of this and you divide by the number of measurements, then the length of the proper motion you're measuring is going to be different from the true length of each of those vectors, simply because you're averaging velocity vectors which aren't collinear to each other. So you can do the calculation, if you're interested, you can do the calculation to see what is going to be the impact of this on your measurement. And you would find that the measurement you're doing is the true value of this orbital motion multiplied by a quantity, which is like this, sometimes called gamma. It's the period of the planet divided by pi times t Gaia, which is 665 days, times square root of 2. All of this times the square root of 1 minus the cosine of 2 pi t Gaia divided by p. And if you look at this quantity here, you can see several things. So first, this goes to 1 when p goes to infinity. And you can expect this because the if you take a long period planet, you can expect that the averaging the data over a small window compared to the orbit of the planet isn't going to change anything. Now, if you look at what happens for p goes to 0, so for very small orbital periods, then this quantity goes to 0, which means that basically if you take a small period and you average your measurements, you're destroying the signal. So this method isn't sensitive to small period planets. And then in between, you have a bunch of zeros when the 665 days from the observing windows divided by the orbital period of the planet is an integer. So if you plot this function, you get something which is like this. So it goes to 0 for small period, goes to 1 for long period planets, and in between you have a bunch of oscillations. So that's a problem for small period planets. You can't really detect them with something like this. If you look at the other extreme for long period planets, so this observing window smearing doesn't really impact long period planets, but you have another effect that you need to take into account, which is that, so you don't truly measure the proper motion of the star with Hipparchus or Gaia, but you also don't really measure the long-term proper motion, because what you really measure is the position of the star at the Hipparchus epoch and at the Gaia epoch. But then this motion of the star is already a combination of the proper motion of the system and the orbital motion of the star. So if the orbit of the orbital period is small, then it doesn't really matter. But if the orbit has a long period, then it's actually very difficult to separate the long-term proper motion of the star from this long orbital motion, this long period orbital motion. And again, you can do the math if you're interested, at least for a circular face on orbit. It's not very difficult to do. And you would find that for long period planets, this anomaly measured with Gaia divided by the true value of the orbital motion is something like pi times the time between Hipparchus and Gaia, so about 25 years, divided by the orbital period. And so that's true in the long period regime, and in between you have to do a proper calculation, which you can do numerically, and you would find something like this, something like the blue curve for the proper calculation. And you can approximate this with a formula like this, and you would get the orange curve. And what you see here is, for this effect, doesn't really change anything for small period planets, but it does reduce the sensitivity of the method at long periods. And so if you combine the two phenomena, you can plot something like this, which would be the sensitivity of the method, of this method. And you would see that basically, so you're not really sensitive to long period planets because of this problem of separating the long-term proper motion from the long period orbital motion. And you're not sensitive to small period planets because of this observational window smearing. So this method is typically sensitive to planets orbiting with orbital periods of, say, from 1 year maybe to 30, 40, 50 years. So that's the typical range of orbital periods at which this method is sensitive. Then in blue, you have the sensitivity for Gaia, and so for the Gaia proper motion anomaly, and in green for the Hipparchus proper motion anomaly. So if you do this, if you get the data from the Hipparchus and Gaia catalog, calculate the proper motion anomaly, then take those effects into account, you can draw something like this, which would be, so for example, for 51 peg, you would find a proper motion anomaly. I don't remember what the value is, but you find a proper motion anomaly for the star, and then this would be the mass of the planet as a function of the semi-major axis, which will be needed to explain this level of proper motion anomaly. And I've also plotted this for another star, HD 206893. I'm going to talk a bit more about this example later on. But so again, you see that the typical range of semi-major axis at which you're sensitive is typically a few astronomical units to 10, 20 astronomical units. That's the typical ballpark. And then you get to masses of maybe a few Jupiter masses, can be less than that for stars which are not too far away from our sun. But that's the range of planets that you can expect to detect with this. Now, there are a number of refinements to the method, especially for stars which are close to our sun, because of many geometrical effects that you need to take into account. But you can also do this for, it works very well for stars which aren't too far away. And this is an example figure which I took from Cavella and colleagues 2019 for Proxima. So again, the same idea, proper motion anomaly has been detected around Proxima. And in this case, it's a close by star, which means that the range of mass to which the method is sensitive goes below 1 Jupiter mass. And so you see the mass as a function of the orbital radius needed to explain the proper motion anomaly of Proxima. And you see that planet B actually cannot explain this proper motion anomaly. So of course, this is related to Proxima C, which I'm going to talk about again just after this. So that would be a way to study some particular targets. If you're interested in one target, then you can get the proper motion anomaly and work with it. You can also look at what happens statistically. If you look at all the data in the Hipparchus catalog and the Gaia catalog, how many planet candidates can you find? And this is again a figure taken from this paper, the same paper, which gives the number of stars around which there is a proper motion anomaly, which translates to a given mass divided by the square root of the radius for different confidence level, 5, 3, and 2. And if you take this and you zoom at the range of masses that we are really interested in today, because we're talking about exoplanet detection, then you see that the number of candidates you have from those catalogs is typically a couple hundreds for confidence level of 5. And if you go down to a confidence level of 2, in the light blue here, you have a few hundreds candidates. So that's typically what you get with the proper motion anomaly observations. Now, again, if you're interested in a particular target, it's not as easy, because then you need to take into account the fact that the orbit can be more complicated than a circular face-on orbit. You can have possibly eccentricity, which I'm not really going to discuss, but you can have, of course, an inclination of the orbit. So you don't really, so in principle, if you could follow the star and get many measurements of the proper motion anomaly, which would translate in many measurements of the orbital motion of the star, you could basically reconstruct the orbit, and you would be able to measure the inclination, the eccentricity, and the true mass of the planet and the semi-major axis, basically everything. The problem is, in practice, you don't have many measurements. You only have 1 or 2 if you have the 2 epochs, Hipparchus and Gaia, but you don't have anything more. And with this, you cannot actually get a measurement of the true mass of the planet, because you have a degeneracy with the inclination and also with the orbital phase. So there are a number of ways to go around this. One of them is to add radial velocity measurements. If you also have radial velocity measurements, then basically you have a measurement of those. So first you have a measurement of the mass of the planet times the sine of the inclination. You also have the orbital period, and you also have the orbital phase from the radial velocity curve. So if you combine this with the proper motion measurement, then you can get the inclination of the planet. And once you have the inclination, of course, you can get the true mass of the planet. So this is a really powerful combination, actually. Even if you have only one proper motion anomaly measurement, if you combine this with radial velocity data, you can still retrieve the inclination and the mass. And this is something which has been done on Proxima C, actually. So this is a plot which I took from a paper by Damaso and colleagues in 2020. So quite a recent paper, where you see the residuals of the radial velocity data after the subtraction of the signal from Proxima B. And here you see the signal from Proxima C. Now, using radial velocity, you can, as I said, measure the orbital period, measure the possible time, the time of the conjunction, and the M sine inclination. So if you take those measurements and you also add the proper motion anomaly, then this is something which has been done also in 2020. You can retrieve the value of the sine of the inclination, and then of course of the true mass of the planet. So a powerful combination. What is also, I think, very interesting is once you have the sine of the inclination, then you start to have actually quite a number of measurements. You know the inclination, you know the period, so you know the semi-major axis, you know the orbital phase. And if you combine all of this, you can actually start to predict where the planet is around the star. So none of those methods, astrometry and radial velocity, is sensitive to the position of the planet. You're just looking at the star. So in principle, you cannot say where the planet is. But if you combine all of this, you can actually start to have an idea. So this is, again, taken from Cavilla and colleagues 2020. Prediction, the probability of the presence of the planet at different epochs and in difference for different orbits, because basically you only have a measurement of the sine of the inclination, so you have two possible values, let's say, for the inclination. But that gives you an idea of where the planet can be. So in this case, unfortunately, you cannot really pinpoint the location of the planet, but I think that's an interesting first step towards being able to predict where the planet is in the sky only based on star measurements, radial velocity, and proper motion anomaly. And I'm going, again, this is important, for example, for direct imaging or long baseline interferometry, where we need to know where the planet is if we want to observe. Now, if you don't have radial velocity measurements, for example, you're interested in a young target where radial velocity is very difficult to obtain properly, so you don't have radial velocity measurements, you can still do something if you have, for example, a direct detection of a planet in the system. Because if you have a direct detection of the planet, then basically you know the orbital phase. So you can also break this degeneracy and get a measurement of the true mass of the planet. And I think an interesting example is HD 206893. So this is a star around which there is at least one giant planet close to a brown dwarf, actually. HD 206893b, which has been observed with direct imaging. And actually, long baseline interferometry, we've observed this target with the exogravity large program. So this is an interesting example, because if you look at the proper motion anomaly, using what I explained before, then for this target, you would get a graph which is a little bit like this. And if you look at the mass of if you look at this planet, then typically you can explain this proper motion anomaly just with this planet B. Now, this is if you look at the proper motion anomaly as a scalar quantity. So meaning you're just looking at the amplitude of this proper motion anomaly. Now, technically, when you measure the proper motion anomaly, you don't have just a scalar quantity. You have a 2D vector on the sky. So you have a proper motion anomaly in alpha, right ascension, and declination. So it's a bit difficult to do this because you have to be very careful with this averaging of the measurements made with Gaia. So you have to take this into account, but you can get a 2D proper motion anomaly. And in this case, because we know where the planet is, because we have those direct imaging observations, so we know the orbit, we know what should be the orientation of the proper motion anomaly. And if you look at the true orientation of the proper motion anomaly, and those figures are taken from a number of papers which are listed here, then you see that the proper motion anomaly generated by this planet B cannot really explain the proper motion anomaly observed from Hipparchus and Gaia. So you actually need another planet in the system to be able to explain this. And so a very recent paper by Jens Kammerer also looked into this, adding gravity observation of planet B, which are very helpful to get a much better orbit estimate. So if you have a good orbit estimate and you have those measurements, then you can actually start to sort of predict where this planet C, should be on the sky. And you can even draw plots like this, where you have the mass that you need for planet B and planet C, depending on the location of planet C, to explain the proper motion anomaly. So you can start to have sort of an idea of what is going to be the mass of B and the mass of C and the location of the two planets, just from this combination of direct observations of B only, not C, and proper motion anomaly. So a very interesting way to start to detect unseen planets around stars around which we already have another planet. So I said that in this case, the exogravity measurements were quite helpful to constrain the orbit. And this leads me to the second part of the talk, which is what can long baseline interferometry bring to those astrometric measurements and those astrometric detection of planets. And probably the first thing which is interesting to say is that if you look at the numbers, so I have here two figures which I took from the Gaia DR3 astrometry paper and the Gaia DR2 astrometry paper. If you look at the numbers, the typical astrometric precision that you have with Gaia depends on the data release, and it depends on the target, especially the magnitude, etc. But it's typically going to be 50 to 200 microarcsecond in DR2 and 10 to 5 microarcsecond if you look at DR3, EDR3. If you look at gravity observations, you also get a typical precision on the astrometry, which is 10 to 50 microarcsecond. So it depends on the orientation of the baseline, depends on a number of things, but that's the ballpark. Now, the difference, of course, is that to get this level of precision, Gaia is averaging a number of measurements, whereas with gravity, you can get this level of precision with a single epoch observation. So you observe during one night and you can get this level of precision. Now, of course, the problem is, so Gaia is observing the entire sky, which is quite nice, whereas with gravity, you have to observe each star individually, so it's more time consuming. But so let me talk a little bit about this, this instrument, gravity, because with this level of astrometric precision, there are a number of things which I think are quite interesting to do for exoplanet detection. But I need to talk a little bit about the instrument in order to be able to talk about the advantages and the problems it raises. So gravity is an instrument on the Very Large Telescope Interferometer. So it can combine the lights coming from the 4 unit telescopes or the 4 auxiliary telescopes. And so it's quite a complicated instrument, so I'm not going to go too much in the details, but I need to talk about a number of things. So it's a fibered instrument, it's a fibered interferometer. So the way it works is the light comes to the telescope. It's collected by the telescope. Then it goes to the delay lines of the Very Large Telescope Interferometer. Then it goes to the instrument, gravity itself. And here you have the light is injected in a single wood fiber. Then you have an OPT control system where you can control the optical path difference between the different telescopes of the array. And then it goes to the beam combiner and to the spectrometer. Now, in the instrument, so there is also an adaptive optics on the telescope. So part of the light goes to the adaptive optics system. So it's an AO corrected fiber interferometer. Now, there are in the instrument two channels. One is the science channels on which you get your science measurements, and the other one is the fringe tracking channel. And the idea is the fringe tracking channel is used to correct the phase errors coming from the atmosphere. So basically, the role of the fringe tracker is to sort of freeze the atmospheric turbulence in terms of phase, so that you can do long integration on the science channel. So this is extremely important, because then you can get rid of this atmospheric distortion of the phase. The problem is, between the science channel and the fringe tracking channel, you can have non-common path errors. So you don't have a good measurement of the phase of your object with this. Which is why in gravity there is also a metrology system. So there is a laser which back propagates into the entire optical train. So it's injected in the science and fringe tracking fiber for each telescope. It back propagates into the entire system all the way to the telescopes. And at each telescope there is a set of diodes on the spider of the telescope, which basically those diodes are gonna see an interference pattern from the light of the laser coming from the fringe tracking fiber and the science fiber. And with this, you can actually measure the non-common path errors in the system. And if you combine all of this, you can actually get measurements of the phase of the object that you're observing there's just an unknown reference point, basically, which is important. I'm going to come back on this later on. So there are different ways to observe with this instrument. One of them, and this is very relevant to what I want to discuss, which is detecting planets with astrometry. So one of them is observing in single field mode. So where basically you're trying to look at a binary. I took this example, a star and a planet. It could be a double star, it could be some other objects. But you're trying to look at something which is below the resolution of a single telescope of the array, which means that the light of the entire object or the entire system that you're observing goes into the fiber, and then you get information on the spatial distribution of the flux from the interferometric measurements. The other way you can use the instrument is in a mode which we call dual field phase referenced interferometry, where basically you're observing a system which is above the diffraction limit of a telescope, of a single telescope. So you put your science fiber on, for example, in this case, the star, and then you move the fiber to the planet and back to the star, back to the planet, etc. And in this mode, so this is something that you can use only because there is this entire metrology laser system and all of this. Because in principle, if you have only one object in the fiber, you cannot measure the relative astrometry between the two. You can only do this because you have this possibility of phase referencing your observations. So if you observe like this, then in principle you can measure the relative astrometry of the two objects. It's also very useful for the direct detection of exoplanets, because of course if you observe in single field mode, then basically you have all the light from the star injected into the fiber. Whereas if you observe like this, when you put the star, the fiber on the planet, then you filter out a significant fraction of the stellar flux. So this is the mode that we've used in the exogravity large program, with which we got a number of results so far. So for example, medium resolution cable spectroscopy on beta peak B, observations of PDS 70 B and C actually. I just put a plot here from a paper by Jason Wong. And of course, the direct detection of the radio velocity planet beta peak C. So all of those results, which I'm not going to really discuss because they are not really relevant to what I want to talk about, which is astrometry. All of those results were obtained in this mode where we move the fiber from the star to the planet and back again on the star, etc. Now, the problem with this is actually when you observe like this, so first off, if you observe something in this mode, then basically you need the system to be below the diffraction limit. So the separation can be at most 60 milliarcsecond for the unit telescope of the VMT. If you observe in this mode, there are a number of factors in the instrument which set a hard limit on the distance between the two objects that you can observe, which is for gravity, it's 2 arcsecond, I believe. So you cannot observe, say, a star here and use a reference point which is more than 2 arcsecond away. Which means that if you want to get astrometric measurements with gravity using this mode, basically you need to observe your target and to find a reference star which is not, so it needs to be bright enough so you can observe it with the instrument, and it needs to be at most 2 arcseconds away from the target. Which leads to many complications, of course, observationally speaking. And this is a plot I took from a paper by Cavella in 2016. This is the trajectory of alpha Cen A and B on the sky. And on the background, you have a J band image. And you see the trajectory of the star on the sky. And you see here, circled in green, you have a number of background sources, which are actually the sources which can be used to do phase referenced astrometry of alpha Cen A or B for the next, 20, 30 years, 20 years, for the next 20 years. So you see there aren't that many targets which can be used. And of course, so basically what happens here is you have a number of observing windows at which you can use to get astrometric measurements on alpha Cen A and B. But it's quite limited, again, because those sources cannot be more than 2 arcseconds away from your main target. So it makes everything quite complicated to be able to do those measurements. But in principle, that's feasible. So you could follow those stars on those windows and get astrometric measurements and potentially detect planets around those stars. The other thing you can do is you can observe a binary. If you have a binary star, then you have an obvious, so you can measure the relative astrometry between the 2 components of the binary, and you can measure the orbit of the binary. So those are 2 examples, 2 binaries on which we can measure the orbit. Again, you have the measurements at the precision of gravity, so typically 50 microarcsecond. And you can try to see a deviation from the 2-body Keplerian motion generated by a planet orbiting around one of the components of the system. Again, you need a binary which you can observe, so the 2 components need to be at most 2 arcseconds away from each other. Makes things complicated, but in theory that's feasible. Now, the interesting part is with gravity, you have a measurement at this level of precision, 10, 50 microarcsecond at each epoch at which you observe. So if you look at the numbers, in theory, this could be a very powerful method. If you look at a star, which is a sun-like star at 10 or 1.34 parsec, and you look at the typical planetary masses that you can hope to be able to detect with this level of precision, then you get to masses which are which can be a fraction of a Jupiter mass. So that can be a very powerful method. If it wasn't for the difficulty of doing the observations, because you need this reference point, this reference target, and all this. Now, interestingly, even when we observe exoplanets, which are relatively faint targets, we do have the same level of precision on the astrometry. We do have astrometry at a level of 50 microarcsecond on those observations of exoplanets. We've demonstrated this on HRA 799E and also on Beta Peak. This is a plot where you have the measurements with different methods on Beta Peak B and C. And you can see the gravity astrometry of Beta Peak C on the 9th, 11th, and February 2020, and on the 7th of March 2020. And it's quite amazing, actually. We can already see the motion of the planet, even between those two epochs on the 9th and on the 11th of February. This is the astrometry and the error ellipse, and you can see the motion of the planet. So we have very good astrometry. Now, if you think about it, if you have the star and a planet orbiting around the star, you can observe the system. So put the fringe tracking fiber on the star, or put the science fiber on the planet, and then you move back and forth. And then you would measure the relative astrometry of the planet relative to the star. Now, if there is another planet in the system, if you observe on another epoch, then of course this planet C will have moved a little bit on the star, but on the sky, but the star also will have moved a little bit because of the reflex motion caused by planet C. So the star is orbiting on an orbit generated by this planet E. So in principle, this relative astrometry is a combination of the motion of C and the reflex motion of the star created by other possible planets in the system. So in principle, basically you have a binary, the star plus the planet around it. It is also a binary system, which is easy to use because usually the planet is at less than 2 arcseconds away from the star. So this is something which we are currently doing with gravity, especially on the Beta Peak system, actually. So using only the gravity astrometry on Beta Peak B, if you fit the orbital motion of Beta Peak B, so two-body Keplerian motion, and you subtract this, then you can actually see in the residuals the reflex motion of the star generated by C, which means that we are at a level with gravity where we can detect planet C only using astrometry on planet B, which is quite amazing, I think. And so you can, in principle, you could measure the mass of C doing this. Now the error bars are quite big, but in this case, because we also have an astrometry on Beta Peak C, if you add this into the mix, then you get a good measurement of the mass of C. Now this is on the Beta Peak system where we know the existence of C. So in some sense, it's of course easier because you know what you're looking for. The next step, which we're going to try to do, is to do this on other systems and to try if we can detect new planets in known planetary system just by looking at the astrometry of the external planet. So basically following an external planet and detecting the reflex motion of the star generated by internal planets in the system. So to conclude this presentation, I'd like to take a step back and talk a little bit about why this is useful, basically, because there are other methods to detect planets. So why is it interesting to also look for planets using astrometry? And I think there are a number of answers to this. One of them is if you look at a mass period diagram and you look at the different methods, transits, radial velocity, imaging, interferometry, and astrometry, then the range of planets, the range of masses and periods on which you can find, at which you can find planets is typically a couple of Jupiter masses and above or below for some targets, and semi-major axis of a few astronomical units. Now, for some formation theories, and I'm mainly thinking about the tidal downsizing, which is sort of an updated version of gravitational instability, they predict, this is just an example, but they predict the existence of an exclusion zone, which is basically a limit at the semi-major axis below which you cannot find, or it's more difficult to have giant planets. Now this, if you do the calculations, if you plug in the numbers, you would find that if you want to test this, then you are looking for planets of Jupiter masses at a few astronomical units. So you're exactly in the range which is best probed by this combination of astrometry with Gaia and Hipparchus. Now, if you look also at the different Gaia astrometry and gravity or classical imaging, I think it's also interesting to see that there is quite a bit of overlap between the two methods, which is very interesting because with astrometry, you can measure the mass of the planet. And with direct imaging or gravity interferometry, you can measure the luminosity of the planet. And we all know that the mass luminosity diagram can be a very powerful tool to test the planet formation theories and the cooling tracks and all of this. So this combination is a good way to start to fill the mass luminosity diagram. So yeah, those observations with Gaia could in principle be followed up by direct imaging or gravity. Now again, the problem with gravity is you need to know where is the planet if you want to be able to observe it. So it's a very powerful instrument because you can observe at small separations, but you need to know where to point the instrument. But again, I've shown that with Gaia, you can hope to be able to find the location of the planet if you have other data, range of velocity, for example. Now, on young targets that you can observe with direct imaging or gravity, it's hard to get radio velocity data. So then we need to find a way to be able to guess the position of the planet from astrometric measurements. So this could be done if you have multiple astrometric measurements in principle, or possibly if at some point we have stellar accelerations, for example, with Gaia, then that would be a very powerful tool to be able to predict the location of the planet and to follow up with gravity. And so we'll have an updated version of gravity in the future, which should improve the capabilities of the instrument. So that should help really to be able to observe the same targets, but the targets on which Gaia planets have been found to observe them with gravity. It will also be very helpful because the maximum separation for this new gravity plus version will not be 2 arcseconds, but will be 30 arcseconds, which means that it will be much, much easier to do high precision astrometry, to find basically a background source which you can use to do the differential astrometry. So that should really help to extend the capabilities of the instrument and to find, hopefully, many, many more planets to test the formation models and all of this. Thank you for your attention.